For homework this week, we're going to start with a silver wire titration. So we have a potentiometric titration with a silver indicator electrode. So we will have a 14.40 milliliter solution of 0.04560 molar silver nitrate. And we're going to titrate that with sodium bromide, and that sodium bromide has a concentration of 0.0250 molar. Now the silver wire is attached to the positive side of a potentiometer, so that tells us that the silver is being reduced. It is the cathode. And we know that the silver, the standard reduction potential for this silver is 0.799 volts. So this is all information that you need to find or know in order to do a problem like this. Now we're asked to find the cell voltage after we have 10.754 milliliters added. So we need to know where we are with this titration. Are we before the equivalence volume, at the equivalence volume, or after the equivalence volume? Because that will change the way that we do this calculation a little bit. But regardless, in order to find that E cell, the E of the cell is always going to be equal to the E of the cathode minus the E of the anode. Now, the E of the cathode is where we're going to be doing our calculation. So the E of the cathode is going to be dependent on the Nernst equation, and we will start with our standard reduction potential voltage and subtract 0.05916 over N. The N in this case is 1. Times the log log of the Q value. So we have products over reactants. The product is a solid. It has an activity of 1. So we just have 1 over the concentration of the silver ion. Then we will subtract from that the voltage of the anode. Now the anode is the saturated calomel electrode because it says right here SCE was attached to the negative side. So you should know or memorize that the standard calomel electrode has a voltage of 0.241 volts. So this is how we're going to calculate the E of this cell, but we need to know where we are in this titration. So let's calculate that equivalence volume. We will start with the volume of our silver solution, and I always convert my volumes into liters. So then I can use my molarity. So that's moles of silver per liter of silver. And then I need the stoichiometry. In order to have the stoichiometry, I need to have my balanced chemical equation for the titration itself. So I will be making silver bromide and sodium nitrate. And we happen to have a 1-to-1 reaction here. So that means we have 1 mole of silver reacting with 1 mole of our bromide. Now I can use the concentration of bromide in order to figure out what that equivalence volume is, and that is per liter of bromide. So the equivalence volume I get for this is 0.02626, and that's a capital L liters, so 26 milliliters, which is 26.26 milliliters. So I am before the equivalence volume. Now, if I'm before the equivalence volume, then the concentration of the silver, which is what I need to find out, that's the missing part of this equation, is going to be dependent on the excess silver. So let's find out how many moles of silver we started with. And in order to do that, I'm going to take the volume of silver and multiply it by the concentration of the silver. And I get that we start with 6.5664, not moles, times 10 to the negative 4 moles of silver. Now, how many moles of bromide have I added? Well, I'm going to take the volume of that as well, multiply it by the concentration, and I get that we have added 2.6885 times 10 to the negative 4 moles of bromide. Now, like with all of our other titrations in equilibria, what we're doing is we are shifting this. So we will be taking this many moles of silver away. So this is a simple subtraction problem, 6.5664 times 10 to the negative 4 minus the moles of bromide give me an excess of 3.8779 times 10 to the negative 4 moles of silver. Now notice how we need to have this in molarity. So I do need to divide this by the total volume. The total volume is just adding these two guys together after they've been converted into liters. So I get a concentration of my silver ion at this point is 0.0154, and it continues, but that's good enough for now. So that is the concentration of my silver. So now I come back up here to my E cell equation, and now I can fill in the concentration of that silver, because that's what all of that calculation was for, 0.0154. And I'm just going to leave this in my calculator. It's easier. And I'm going to crunch those numbers. And I get an E of the cell at this point in the titration is equal to 0.451 volts. Now the system wants you to put this in scientific notation. So put 4.51, and then this would be to the negative 1. It doesn't want you to put in a unit for this particular problem. For number 2, we actually have the same titration here, but we have some different values. So again, we're going to need to calculate where we are in the titration itself, before, at, or after the equilibrium volume. So let's write down these conditions. We have an 11.20 milliliter sample of 52800 molar silver nitrate, and we're titrating it with 45.71 milliliters of a 0.0250 molar bromide solution. So still, we need this equation, but now the calculation to find our concentration of silver is a little bit different. So let's start by finding out how many moles of silver we have. Well, we should do the VE calculation first. I'm just going to run through that real quick, but I happen to know we're pretty far beyond the equivalence volume at this point. So I've calculated the VE. The VE is 23.65, and as you can see, we're pretty far after that. So what we have done is we've taken our silver ions and we have added to it more than enough bromide in order to force the making of silver bromide. So whatever silver is left in solution, it's because this solid is at equilibrium. So when we write a KSP, we write it as the solid breaks into its pieces. Now at this point, there is solid. We know there's solid. And we also know that we're going to have a little bit of this silver ion, but the silver ion's concentration is purely going to be dependent on what the solid gives up. Now the bromine, we have excess bromide in solution. So we need to find that concentration because we're going to end up adding X to it. So in order to find how much bromide we have in solution, we need to know what we started with. So for moles of the bromide, we're going to take the volume and we're going to multiply it by the concentration. And again, this is for the bromide. And I get 1.14. I'm going to give you all the digits in my calculator because I'm going to end up leaving them in my calculator anyway. Times 10 to the negative 3, that's moles of the bromide. Now, how many moles of the silver did we start with? Well, we take the volume of silver and we're going to multiply it by the concentration of silver. And in this case, we started with 5.9136 times 10 to the negative 4 moles of silver. So we have consumed all of that silver, and we consume that in a 1-to-1 relationship. So I take the amount of bromide that I have, 1.14 times 10 to the negative 3, and I'm going to subtract the moles of silver, because what that represents is the excess bromide in solution. So I have 5.51 times 10 to the negative 4 moles of bromide in excess. And I need to divide that by the total volume in liters. So the total volume at this point in the titration is 56.91 milliliters. So the concentration of the bromide that I started with, which is what I was calculating, the concentration of the excess bromide in solution is then equal to, I have 9.68 times 10 to the negative 6. Now I need to then equate this to the KSP, because remember the KSP is going to be equal to the concentration of the silver ion times the concentration of the bromide ion. So I fill that in. The KSP for silver bromide is 5 times 10 to the negative 13. X represents the concentration of silver, and then the bromium, or the bromide, is represented by 9.68 times 10 to the negative 6 plus X. Now, this is one of those situations where you can simplify and solve for X. So then X is equal to 5.16 times 10 to the negative 8 molar. Now again, that is the concentration of the silver. All of that is done in order to then turn around and put that value right here. Now we're still working at the cathode. The silver is still at the cathode, but now we have 5.16 times 10 to the negative 8 molar for our concentration of silver. So when I crunch all those numbers together, I get an E of the cell is equal to 0.12. I actually get 269, so I would round that to 0.127 volts. Again, we are asked for scientific notation and no unit. For number 3, we're asked to consider this cell and then calculate the voltage. So you have to understand this cell notation. The left side is the anode. So at the anode, it looks like I have hydrogen at a particular pH. And then, so the anode is H2 gas at 0.100 bar. And we have hydrogen ion. And that is at a pH, so we can get the concentration of 2.82. And at the cathode, now I'm leaving this undone on purpose. So at the cathode, I have the chloride ion at a concentration of 0.194 capital M molar. And then I have mercury, solid mercury, Hg2Cl2, and liquid mercury. Well, what if that stops me? What if I can't remember how these things react? Well, if you go to your standard reduction potential table, which is located in the classroom, and look for mercury, and this is in alphabetical order by element. So mercury starts with an M. What I'm looking for is the H2Cl2 as a solid. I'm looking for some liquid mercury and the chloride anion. So it looks like we might have a saturated calomel electrode, but then again, we might not. Now let's go back to that question real quick. That question had a specific concentration of chloride. So I'm going to go with it's not saturated, and I need to use this equation with this reduction potential. Now for the anode, I have hydrogen and I have a hydrogen ion. So let's scroll up to hydrogen and see what we can find. We need something with the hydrogen gas and a hydrogen ion. So I'm going to be using this equation right here. 2H plus 2 electrons is H2 gas. And the standard reduction potential for this is 0, because this is our standard hydrogen electrode. So now we need to figure out how we're going to get to the E of the cell. Well, we're going to use Nernst. We're going to use the cathode minus the anode. And we're going to need to pay attention to which are our products and which are our reactants. Now, when we write our equations out as reduction, like this, then if you write everything out as reduction, your products will always be on the right and your reactants will always be on the left. And then using Nernst should become intuitive. So I'm going to do this as one large equation. Okay, so the E of the cell is going to be equal to the E of the cathode minus the E of the anode. That's always the way it is, but we don't have just standard conditions anymore. That's why we need Nernst. So the E of the cell is still going to be the E of the cathode minus the E of the anode, but the E of the cathode is going to be represented by the standard reduction potential, 2.68 volts, minus 0.05916, our constant, divided by N is the number of electrons, times the log of the Q. The Q is the concentration of the products. In this case, we have a concentration here. This is a liquid, and this is a solid. So we're going to be using the concentration of the chlorine, which is going to be squared. So 0.194 squared, and it's squared because of this coefficient. Now, the activity of the reactants at this point is 1. So this represents the E of the cathode. Now the E of the anode, I'm actually going to write that on another line because I think I'm going to run off the screen. So the E of the anode starts with the standard reduction potential of the anode minus 0.05916 divided by N, which is 2, and that's found right here, times the log of the Q. The Q is going to be represented by the pressure of the hydrogen gas in bars divided by the concentration of the hydrogen ion squared. Now, the pressure of the hydrogen gas is given to you in bars. That's convenient, so 0.100. But that concentration of the hydrogen ion isn't directly given to you. You need to calculate it. So you're told the pH is 2.82. And you need to calculate what is that hydrogen ion concentration. Well, pH is equal to the negative log of the hydrogen ion concentration. So you need to be able to put this in your calculator and generate that pH. That concentration of hydrogen. So I'm raising 10 to the negative 2.82, and I get the concentration of the hydrogen is 1.51 times 10 to the negative 3, and the unit for that is a capital M molar. So that goes in here for the concentration of hydrogen, 0.51 times 10 to the negative 3, and we will end up needing to square it. Again, that square comes from the coefficient of the balanced chemical equation. Now, there are several places where you can screw up this calculation, so be sure to take it stepwise, take it slow, and double check your work. So for the E of the cathode, when I do this calculation, for the E of the cathode, I get 0.310 volts, and for the E of the anode, I get a negative 0.137. So the E of the cell is still the E of the cathode minus the E of the anode, and the E of the cell is then 0.447 volts. Now the system would like this in scientific notation, so 4.47 times 10 to the negative 1, and this time we need our units. The units are volts. That's a capital V. Now for question 4, we're asked to find the solubility product of magnesium hydroxide by using these equations. Now this is analogous to using Hess's law for enthalpy. So I'm aiming for, and it's spelled out for us right here in case there was any question, what I'm aiming for is taking this solid and putting it in equilibrium with its ions. And I need a 2 there. There's a 2 that's missing from here, so I'll have to go back in and correct that. But this is what we're aiming for. That's our target. So what I have is magnesium ion on the left side, on the reactant side. I have magnesium ion plus 2 electrons reacts to form that solid magnesium. Well, I want the magnesium ion over here on the product side, not the reactant side. So I'm going to flip this around. I'm going to take this and switch it. So I have Mg solid is in equilibrium with 2 electrons and the magnesium ion. Now that takes my negative reduction potential, 2.36060 volts, and makes it an oxidation potential. So what I'm doing is I'm actually changing the sign. So the E of this equation is now 2.360 volts. Now for the other equation, I want it written just as it is. I want the magnesium hydroxide to be on the reactant side, 2 electrons in equilibrium with magnesium solid and 2 hydroxide ions. Looks like my negative sign kind of tapered off. But that E is going to be equal to a negative, I just realized I'm off the screen, so that E is equal to a negative 2.690 volts. Now when I add these two equations together, the 2 electrons cancel out, as do the 2 solid magnesiums. And what I'm left with is my target equation, MgOH, OH2, so 2 OHs in equilibrium with the magnesium ion and 2 hydroxide ions. So what do I do with the E's then? Just like with Hess's law and enthalpy, now I'm going to add these E's together. So the E is of this reaction is now going to be negative 2.690 plus 2.360 will give me a negative 0.330 volts. I actually went through my homework and I went to render the video before I realized that I didn't finish this problem. So I imagine there's going to be a few of you who might make the same mistake. So I'm going to interject this part, hopefully to keep you all from making that mistake. So I calculated the E, and that's fantastic, but the question asked for the K. And our equation is that the log of the K value is going to be equal to N E over 0.05916. So now that I have the E, we can fill this in. And the N here is 2, because we're trading 2 electrons. The E is what I calculated, negative 0.330. So in order to find the K, I take 10, I take the antilog, which is 10 to this as my exponent. And when I do that, I get the value I get is 6.97, and it continues, 6.979 times 10 to the negative 12. If you're going to round this, it would actually be rounded to like 7.0 times 10 to the negative 12. If you want to have 3 significant digits, that's okay. I'm not going to count you off for it. 6.98 times 10 to the negative 12, but that is the value of the K that we're looking for in this problem. So that's what you would write in this box, hopefully giving me some work. I take handwritten work all the same, so don't feel like you need to type it all out. And for the last question, we're going to use the selectivity coefficient. So we're told that K, the selectivity coefficient, is 5 times 10 to the negative 3. That's a reasonable selectivity coefficient. It's relatively small. When this electrode is placed in a lithium solution of this magnitude, the potential is something specific. What would the potential be if sodium were added to give this concentration of sodium ions? Well, without the sodium, what we're looking for the constant. Remember, what we're doing with a selectivity coefficient when we have something like this is we need to start with the voltage without an additional ion. So the potential, I used what was in the book. The potential is a negative 0.500 volts. And what we're going to do is solve for the word constant, because that constant will need to be used in order to calculate what would happen once we add the sodium. So we have lithium plus 1 electron becomes lithium, so our N value is 1, therefore we have 0.05916 times the log of the concentration of that lithium. So the concentration of the lithium that I was given was 5.584 times 10 to the negative fourth. So I'm going to solve for the word constant, just with standard algebraic principles. So when I solve, I get that the constant for this particular electrode is going to be 0.3075. I'm just going to keep those as my digits. So now I can solve for the potential. So the potential I'm looking for is going to be equal to my constant, 3075, plus 0.05916. And here's the tricky part, times the log of, and we need to add the moles of our, not the moles, but the molarity of our ions together, using that selectivity coefficient. So the concentration of our lithium, 5.584 times 10 to the negative 4, plus, then I use my K value, 5 times 10 to the negative 3, and then I'm going to multiply the concentration of my sodium by that K value. So 0.124. So then the E, after we've added the sodium in, is 0.134 volts. We're asked for our answer in scientific notation, so 1.34 times 10 to the negative 1.